Hello everyone, my name is Rafael. I am an electrical engineer, and in this video I would like to invite you to watch the solution of 27 problems related to electromagnetism as a preparation for college and civil service exams. Let's go to the first exercise number 1. Calculate the electric force exerted by Q1 on Q2. If Q1 is 3 times 10 to the minus 4 coulomb, located at M1, 2, and 3, and Q2 equal to negative 10 to the minus 4 coulomb, located at N2, 0, and 5. In a vacuum. Okay, my friends, this is the exercise. Let's go to the solution. The electric force exerted by Q1 on Q2 can be found by F2, the force on Q2 is equal to Q1, Q2 divided by 4 pi epsilon 0 R12 squared A12, where A12 is a unit vector in the direction of R12. You see R12 here, so A12 is a unit vector in the direction of R12, and it is of the sort it can be calculated as R12, this vector here, divided by its magnitude, and since we have that R1 plus R12, R1 plus R12 is equal to R2, which means that R12 is equal to R2 minus R1. We are going to use this, so this unit vector here can be written as R2 minus R1 divided by R2 minus R1. The magnitude, it is the factor divided by its magnitude, because this is a unit vector. Okay, now we are going to calculate this unit vector here. R12, this vector here, that positions the force, that gives the direction of the force, and represents the distance between the charges, is going to be equal to R2 minus R1, which is equal to R2 is 2 in the x direction plus 5 in the z direction minus R1, 1 in the x direction plus 2 in the y direction plus 3 in the z direction. And if we develop, we get that R12 is a x minus 2ay plus 2az. Okay? Now we have to calculate the magnitude of this vector. The magnitude is going to be 1 squared plus negative 2 squared plus 2 squared, and this is 3. Consequently, A12 is going to be ax minus 2ay plus 2az divided by 3. Now, all we need to do is to calculate the force using this expression here, and we know that F2 is equal to 3 times 10 to the minus 4 Coulomb times negative 10 to the minus 4 coulombs divided by 4 pi epsilon 0 1 over 36 pi times 10 to the minus 9 times the vector squared. The magnitude of the vector is 3. The magnitude of the vector is 3. So here it is 3 squared. And we have to multiply all this by this vector here, which represents the direction ax minus 2ay plus 2az divided by 3, and this is going to be equal to negative 30 ax minus 2ay plus 2az divided by 3. Okay, so this is the force. This is the solution. This is the force exerted by Q1 on Q2. And the magnitude of the force is 30. The magnitude of the force is 30 newtons. And the direction is given by this vector here. This vector here. You see that they are of different polarities. This is a positive charge, this is a negative charge. So this negative sign here represents attraction. Okay? When calculating force, you discover a negative sign. It represents attraction. This is a negative charge, this is a positive charge. Different charges or charges of different polarities attract each other. Okay, this is all for exercise 1. Let's go to exercise 2. Exercise 2 now. Calculate the magnitude and the direction of the electric field at P caused by 4 identical 3 nanocoulomb charges located at P1, P2, P3, and P4 as shown by the figure. Okay, my friends, this is the diagram, and let's calculate the electric field at P caused by these 4 charges. Okay? To help us calculate, let's call R1 equal to Rp minus R1, the vector that positions the influence or the electric field at P caused by Q1. Okay? R1 positions Q1 and RP positions the point. And R1 is the vector that goes from Q1 to the point P. Similarly, we're going to do for the other charges. R2 is RP minus R2. R3 is RP minus R3. And R4 is RP minus R4. Okay? With these vectors, we can calculate the electric field using this expression here. E is equal to the summation from 1 to n of Qm over 4 pi epsilon 0 r mp squared in the direction of AMP. Okay? Alright, so we are going to sum the contributions of the fields caused by all the charges. And to do this, we need to work with these vectors here. Okay? And this vector here is going to be the difference between the vector that positions the point P, which is RP, minus the vector that positions charge 1. Okay? This is AX plus AY plus AZ, and this is AX plus AY. For this point, AZ is 0. So the difference between them is AZ only. The same is going to be done for charge 2. Okay, R2 is AX plus AZ plus AY plus AZ minus AX plus AY. And this is 2AX plus AZ. Similarly, AX plus AY plus AZ minus AX minus AY and 0 AZ. And this is 2AX plus 2AY plus AZ. And the same will be done for R4, and this is 2AY plus AZ. Okay? With these vectors, we are going to calculate the field using this expression here, and it is the electric field at P is going to be 3 times 10 to the negative 9 divided by 4 pi times 1 over 36 pi times 10 to the negative 9 multiplying now the unit vectors. The unit vectors are, for this direction, AZ divided by the magnitude. The magnitude here is 1. Okay? The square root of 1 squared is 1. times here you observe that we have to multiply by the magnitude squared. 1 squared is 1. So is 1 squared. The same is needed for this. We sum this, 2ax plus az, and we are going to divide by the magnitude of this because we are working with unit vectors here. We are working with unit vectors. So to make a vector a unit vector, we have to divide it by its magnitude. The magnitude here is the square root of 5. The square root of 5. 2 squared is 4, plus 1 is 5. The square root of 5 is the magnitude of this vector here. And as we need to multiply by the square of the magnitude, it is 1 over 5. Okay? We're going to do it for all the vectors. For R3, 2ax plus 2ay plus az. The magnitude is going to be 3, okay? It is going to be the square root of 2 squared plus 2 squared plus 1 squared. It is then the square root of 9, which is 3, okay? This is the unit vector. This is the unit vector. This guy here. And we have to multiply by the magnitude of the vector, which is 1 over 9. And for R4, it's going to be 2ay plus az divided by the square root of 5 times 1 over the square root of 5. Now, the square root of 5 squared, which is 5. If we develop this, we get that, we continue developing, of course, and we get that this is equal to 34.2 in the direction of 0.199ax plus 0.199ay plus 0.959 Az volts per meter. This is the magnitude as the exercise required. This is the magnitude of the field, and this is the direction. This is the direction of the field. Okay? Here is 9. This is the magnitude of the field, and this is the direction of the field. The exercise wanted us to calculate the magnitude and the direction of the field. Okay, my friends? This is all for exercise 2. Let's go to exercise 3 now. Exercise 3. 2-point charges of magnitude 3 times 10 to the negative 9 coulomb and minus 5 times 10 to the negative 9 coulomb are 2 meters apart. Determine the magnitude of the force between them and state whether it is attractive or repulsive. Okay, my friends, let's go to the solution. To calculate the magnitude of the force, we use F equal to K Q1 Q2 divided by R2. And we know the exercise provided us K is 9 times 10 to the 9th watts meter squared per coulomb squared. We're going to use this constant, and the magnitude of the force is going to be 9 times 10 to the ninth times 3 times 10 to the negative 9 times negative 5 times 10 to the negative 9. It all divided by 2 squared, and this is equal to negative 3.37 times 10 to the negative 8 newtons. Okay, this is the magnitude of the force. Okay, now the magnitude. The magnitude of F is 3.37 times 10 to the negative 8 newton. Alright? And we have a negative number here. What does it mean? When you calculate the forces and you discover a negative number, it means that they are attractive. The force is attractive, which means that one charge is going to attract the other. Alright? So this is exercise 3, a very simple exercise that requested from us the magnitude of the force and to state whether it is attractive or repulsive. Okay, my friends, this is all for exercise 3. Let's go to exercise 4 now. Exercise 4 now. Calculate the total charge contained in a 2 centimeter length electron beam as shown by the figure. So this is the electron beam, and the length of the electron beam is 2 centimeters as expressed here by the height of this cylinder, and the volume density of charge is negative 5 times 10 to the negative 6 times e to the negative 10 to 5 rho z. Okay, we are going to calculate the total charge by integrating the volume density of charge. So the solution is the triple integral of rho v dv. Okay, but we are not going to integrate in Cartesian coordinates. It is a lot harder to do this, as it is a cylinder. Much better to integrate using cylindrical coordinates. Then, as the radius of the cylinder is 1, then rho is going to vary from 0 to 0.01 meters. Okay? In cylindrical coordinates, instead of using x, y, and z, we use rho, phi, and z. Phi is the angle, and it is going to vary from 0 to 2 pi. Okay, the entire circle, 2 pi. And z is going to vary from the top, from the bottom of this cylinder to the top. From the bottom to the top. From the bottom to the top. Z varies from the bottom to the top. And then, to calculate the total charge, we simply need to integrate. We're going to integrate from 0.02 in z to 0.04 in z. of the integral from 0 to 2 pi in phi, and from 0 to 0.01 in rho of -5 times 10 to the -6 times e to the -10 to 5 rho z rho de phi de z. Okay? And by developing this, we get that Q is equal to 0.078 picocoulombs. Okay, my friends? This is the solution of exercise 4. Let's go now to exercise 5. Exercise number 5 now. Calculate the electric flux density 3 meters away from a uniform line charge of 8 nanocoulombs per meter. Okay? This is the uniform line charge, and we want to calculate the electric flux density 3 meters away from it. But before understanding this, it is prudent to firstly understand this. Okay? To understand the field of a line charge, it is necessary to understand firstly the contribution of a differential element of charge. Okay? And let's understand it. Let's understand the contribution of this differential element of charge. Okay, we are going to locate the differential element of charge with this vector RQ, and we want to measure the field produced at P. And we are going to locate the point P with the vector RP. And this vector here that goes from the differential element of charge to the point is called R. And R is RP minus RQ. Okay? And the magnitude of R is the magnitude of RP minus RQ. Okay? And the electric field produced is dE equal to dQ divided by 4 pi epsilon 0 r squared. Okay, this magnitude here is squared, and AR. But AR is the unit vector in the direction of R. Okay? How do we find AR? We simply divide the vector R, which is RP minus RQ, by its magnitude, which is the magnitude of RP minus RQ. Okay? And this in polar coordinates is going to be RP in polar coordinates is rho a rho, and RQ in polar coordinates is z AZ. And thus the field, this field here in polar coordinates is L. Okay, this element of charge dz 4 pi epsilon 0 rho a rho minus z AZ divided by rho squared plus z squared raised to the power of 3/2. Okay? And as the field contributions cancel each other out in the z direction, we need to integrate. We need to integrate in z, okay? Because this is only for this element of charge, this differential element of charge. If you want the entire line of charge, we need to integrate this in z. And if we integrate this in z, we get that E P is equal to rho L over 2 pi epsilon 0 rho a rho. Okay, this is the expression that we are going to use here to calculate the electrical flux density 3 meters away if rho L is equal to 8 nanocoulombs per meter. Alright? And we are simply going to use this expression here that I just demonstrated to you. And we're going to find that E at P is going to be equal to 8 times 10 to the minus 9 over 2 pi times 1 over 36 pi times 10 to the negative 9 rho a rho. And it is going to be 143.8 over rho in the a rho direction. In the a rho direction, volts per meter. And by using that rho is equal to 3 meters, because we want to measure the field 3 meters away from the line of charge, we find that the electric field is equal to 47.9 in the a rho direction, volts per meter. And now we are going to use the property that says that D is equal to epsilon 0 times the field. And by doing this, we discover that D is equal to rho L over 2 pi rho in the a rho direction, and this is equal to 0.424 a rho nanocoulombs per meter. Okay, this is the solution of the exercise. The exercise wanted us to calculate the electric flux density D 3 meters away from a uniform line of charge of charge density equal to 8 nanocoulombs per meter. Okay, and the answer is this value here in the a rho direction. The a rho direction is this direction here that goes away, pointing away from the charge. Alright? This is all for exercise 5. Let's go to exercise 6 now. Exercise 6 now. Determine the flux density D at 403 if there is a point charge of negative 5 pi microcoulombs at 400 and a line charge of 8 pi microcoulombs per meter along the y-axis. This is the exercise. Let's go to the solution. The flux density at D will be the sum of both contributions, the contributions of Q0, which represents the point charge, and the QL, which represents the line charge. So D will be equal to D 0 plus DL. Okay? Let's calculate each, and then finally we are going to sum them. For the point charge, we're going to use that D is equal to epsilon 0 times the field, which is going to be equal to Q over 4 pi r squared in the AR direction. This is a unit vector that positions this vector here, the vector that goes from the charge to the point where we want to measure the field. And this can be rewritten as Q over 4 pi r minus r0 over r minus r0, the magnitude of this vector cubed. Okay, r0 is this vector here, all right, and r is this. R positions the point, r positions the point, and r0 positions the charge. R minus r0 is this vector here that goes from the charge to the point, okay? And we use r and r0 in this expression in this form. And r will be equal to 4 in x, okay, 4 in the ax direction, 4 in the ax direction, plus 3 in the az direction, and r0, which positions the charge, is simply 4 in the ax direction. And this vector here that represents r minus r0 is r minus r0 is equal to 3 in the az direction, and its magnitude is equal to its magnitude cubed. Its magnitude cubed is 27. Okay? Using the expression, we can simply substitute the values here. Minus 5 pi times 10 to the negative 3 times 3az divided by 4 pi times 27 is equal to minus 0.139 az in the az direction microcoulombs. So this is the flux density due to the point charge. Now let's do the same for the line charge. Okay? And after we calculate this for the line charge, we are going to sum the values for the line charge. For the line charge, VL is equal to rho L over 2 pi rho A rho. Okay? And A rho, which is a unit vector, we get that A rho is going to be the vector that positions the point minus the vector that positions the charge, which is going to be 4ax plus 3az. And this is divided by the magnitude of the vector 4 squared plus 3 squared. And this is 4ax plus 3ay divided by 5. And if we develop this, you're going to get that dl is going to be 8 pi. The charge is 8 pi microcoulombs per meter divided by 2 pi times 5 times 4ax plus 3az divided by 5. Okay? And this is 0.64 in the AX direction plus 0.48 in the AZ direction microcoulombs per meter squared. Okay? Then we need to sum this with this. Alright? And finally, the answer of the problem, the solution, is going to be summing this with this. We get that D at P is 640 in the AX direction plus 341 in the AZ direction microcoulombs per meter squared. Okay? This is not micro, this is not, this is a milli, this is a milli, this is a microcoulombs per meter squared, okay? Observe that I multiplied this by 1,000. I multiplied this and this by 1,000. Here it was in millicoulombs per meter squared, multiplied it by 1,000 for a better visualization. And this is not in millicoulombs, this is in microcoulombs, okay? This is a solution of exercise 6. Let's go to exercise 7 now. Exercise 7, calculate the charge density, the electric field, and the flux density for a 50 centimeter coaxial cable having in a radius of 1 millimeter and another radius of 4 millimeters. Assume the space between the conductors is filled up with air and that the total charge on the inner conductor is 30 nanocoulombs. Okay, this is the configuration. The inner radius is A and the outer radius is B. And we begin by finding the surface charge density on the inner cylindrical conductor. S for the inner conductor is going to be Q inner divided by 4 pi AL. And this is equal to 30 times 10 to the negative 9 divided by 2 pi 10 to the negative 3, 0.5. Okay, because the exercises say that the length of the cable is 50 centimeters and that the charge on the inner conductor is 30 nanocoulombs and the radius of the inner conductor is 1 millimeter. And we use this here, 1 millimeter, 50 centimeters, and 30 nanocoulombs, and we get that the total surface density of charge is equal to 9.55 microcoulombs per meter squared. Okay, this is for the inner conductor. Let's calculate the same for the outer conductor. And we compute the charge on the surface of the outer conductor and we divide by 2 pi BL. The exercise said that B is 4 millimeters and L is the same, 50 centimeters, and we get that, observe that they have different polarities. For the inner conductor, the charge is positive, but for the outer conductor, the charge is negative. So it is negative 30 times 10 to the minus 9 divided by 2 pi times 4 times 10 to negative 3 times 0.5, and this is negative 2.39 microcoulombs per meter squared. And the internal fields can be calculated as we observe that dl, the flux density, is equal to rho L divided by 2 pi rho in the A rho direction. Okay, and since rho L is equal to 2 pi A rho S, okay, we have a surface density of charge, and we multiply by the surface of this cross-sectional area here, this circular cross-sectional area, we have the element, the line element. Okay, we have, for example, this is the conductor, and this line element here, okay, this DL here can be written as this: the surface times the cross-sectional area, the circular cross-sectional area, And in this way, the expression becomes D equal to A rho S divided by rho. Understand that this seems kind of strange, but this rho S here is the surface density of charge, and this rho here is the radian distance from the conductor, okay? The radian distance from the conductor. And using this expression, we find that D is equal to 10 to the negative 3 times 9.55 times 10 to the negative 6 divided by rho, which is equal to 9.55 over rho nanocoulombs per meter. In the AX direction, in the A rho direction. And the electric field is going to be D over epsilon 0, and this is 1079 over rho volts per meter. The expressions apply to the region where? To the region within the to the region here, away from the out of the inner conductor, but within the inner conductor. The expression applies for 1 rho 4 millimeters, and if rho is less than 1 millimeter, or if rho is greater than 4 millimeter, then both E and D are equal to 0. Okay, so this result here and here apply only to this region here, outside of the inner conductor, but inside of the outer conductor. Okay, my friends, this is all for exercise 7. Let's go to exercise 8 now. Exercise 8, calculate the divergence of D at the origin if D is equal to e to the negative x times the sign in the AX direction minus e to the negative x times cosine y in the AY direction plus 2z in the AZ direction. Okay, this is the exercise. Let's go to the solution. And the divergence of D is equal to the partial derivative with respect to x of this dx plus the partial derivative with respect to y of dy plus the partial derivative with respect to z of dz. Who is dx? This is dx in the x direction. Who is dy? This is dy in the y direction, and this is dz in the z direction. And we simply calculate this. The derivative of this with respect to x is, so the divergence of D is going to be the partial derivative of this with respect to x is negative e to the negative x sine y plus the partial derivative of this with respect to y is e to the negative x sine y, and the partial derivative of this with respect to z is simply 2. And at the origin x, y, and z are all equal to 0, and putting 0 here, 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 and here, we find that the divergence of the flux density at the origin, according to this expression here, is 2. Okay? Very simple exercise just to practice using the expression for the divergence. This is all for exercise 8. Let's go to exercise 9 now. Exercise number 9. Evaluate both sides of the divergence theorem for the flux density d equal to 2xy in the x direction plus x squared in the y direction, Coulomb per meter squared, in the rectangular parallelepiped formed by the planes x equal to 0, x equal to 1, y equal to 0, y equal to 2, z equal to 0, and z equal to 3. Okay, my friends, this is exercise 9. Let's go to the solution. As there is no field in the z direction, okay, we have a field in the x direction, in the y direction. As there is no field in the z direction, we are going to evaluate for the following surfaces. Okay, we have the front here. We have the front here in the ax direction. We have the back in the negative ax direction. We have the side here. In the positive y direction, and we have this other side here in the negative ay direction. And we are going to use these surfaces to integrate the flux density to calculate the total flux. And yes, and this surface integral can be split into 4, and is going to be the integral from 0 to 3, from this integral from 0 to 2 of d for the surface x equal to 0, this surface here, x equal to 0, with the vector pointing in the negative x direction. dz dy, we are integrating in y first, okay? dy dz in the negative ax direction plus the integral from 0 to 3, the integral from 0 to 1 to 2 of the flux density for x equal to 1. X equal to 1 is this here, this surface in the positive x direction, dx dz, in the ax direction, dy is in the ax direction, and here we are going to integrate along the sides here as these surfaces are showing, integrating from 0 to 3 and from 0 to 1 for y equal to 0 first, dx dz in the negative y direction, plus the integral from 0 to 3, the integral from 0 to 1 of the flux density for y equal to 2, dx dy in the ay direction. And if we carry out these integrals here, this, and this, we get that this surface integral is equal to the negative of the integral from 0 to 3, the integral from 0 to 2 to xy, okay, because we are integrating for in this expression here for x, okay, dx. When x is equal to 0, we are integrating in the x direction. Because it is a dot product here, a dot product between ax and ax is either 1 or negative 1. With y, it is 0. So for us, it is going to be the negative, all right, because this is in the positive ax direction and in this negative ax direction. And the same is going to be done for the others. The integral from 0 to 3 of the integral from 0 to 2 to xy dy dz x equal to 1 plus the negative zero to 3, 0 to 1, x squared dx dz for y equal to 0, okay? We are integrating now this one here, the third, okay? We are integrating in the ay direction. For the ay direction, this is 0, and this is a dot product. Ay in a dot product with a negative ay is a negative number. That's the reason this negative number here. and plus the integral from 0 to 3, the integral from 0 to 1, x squared for y equal to 2, dx dz, and if we do this, we know that the x here, for x equal to 0, we put 0 here, and this becomes 0, and this becomes 0. And since dy for y equal to 0 is equal to dy for y equal to 2, these two guys here cancel out each other as well, and then we are left only with this. Okay, this is this. We are left only with this, okay, and the result is 12. The final result is 12. All right, this is the solution. There is another way of calculating this. The exercise wanted us to evaluate both sides of the divergence theorem. This is one side of the divergence theorem. We are going to evaluate the other side of the divergence theorem and hold this, that the result is 12. The other side of the divergence theorem says that the triple integral of the divergence of D is equal to the charge, to Q, or the flux density. Okay? So we need to calculate the divergence of D first. Okay, the divergence of D is equal to the partial derivative with respect to x of dx plus the partial derivative of y with respect the partial derivative of dy with respect to y, and we don't have the z component here. Okay, the derivative of this with respect to y, with respect to x, is 2y. Okay, so it is going to be 2y plus the partial derivative of this with respect to y is 0. So the solution is only this. Okay? The divergence of this vector here is 2y. Now we need to integrate. We are going to integrate from 0 to 3, from 0 to 2, and from 0 to 1 of 2y dx dy dz, and this as well gives 12. And we have evaluated both sides of the divergence theorem. All right? Firstly, using both sides of the divergence theorem. This is These are the both sides of the divergent theorem, and this is what we calculated, and it is all for exercise 9. Let's go to exercise 10 now. Exercise number 10. Determine the work expended in carrying 2 coulombs of charge from B to A along the shortened arc of the circle x squared plus y squared equal to 1 at z equal to 1. Okay, the circle is this, but it is not going to be on the xy plane. It is going to be raised by 1 along the z direction. If the electric field in the region is E equal to y in the x direction plus x in the y direction plus 2 in the z direction. Okay, my friends, this is the exercise, and the solution is the work exerted in carrying 2 coulombs of charge from B to A along this curved path is going to be negative Q from B to A E dl. Okay, this is a line integral, and it consists of working with the field in this direction and the parametrization of the curve. And let's do it. Let's work with it. So the work is going to be negative 2. Okay, we are carrying from B to a charge of 2 coulombs from B to A, and the field is yx plus xay plus 2az in a dot product with this curve here, dx ax plus dy ay plus dz az. Okay, and the work becomes negative 2 times the integral from B to A of y in the x direction plus x dy plus 2 dz, and by understanding that due to the shape of the curve, we know that x squared plus y squared is equal to 1. So y is equal to 1 minus x squared, and x is equal to the square root of 1 minus y squared. And the work is going to be minus 2 integrated from the integral from 1 to 0.8 y dx minus 2 times the integral from 0 to 0.6 minus 4 times the integral from 1 to 1 dz, and this is negative 0.96 joules, and this is the work that need to be expended to carry 2 coulombs of charge from B to A following this curve in a region where the electric field is this. Okay, my friends, this is all for exercise 10. Let's go to exercise 11. Exercise 11, given the potential field V equal to 2x squared y minus 5z, in the point P, -4, 3, and 6, find at P, letter A, the potential V, letter B, the electric field E, letter C, the electric flux density, and letter D, the volume density of charge. Okay, so let's go to letter A now. The solution. The electric potential at P is going to be found by applying this here. Okay, it is easy. We simply multiply 2 times -4 squared times 3 minus 5 times 6. Okay, and we find therefore that the potential at P is 66 volts. Letter B now. Letter B wants us to calculate the electric field. The electric field is going to be calculated by the gradient of V. Okay? It is the negative of the gradient of V. Observe that V is a number. It is a scalar, while E is a vector. Alright, we use this operator to convert a number into a vector. So the gradient, the negative of the gradient is going to be the partial derivative with respect to x in the ax direction plus the partial derivative with respect to y in the ay direction plus the partial derivative of the potential with respect to z in the az direction. Alright? And if we take the partial derivative of this, the partial derivative of v with respect to x is 2xy. No. The derivative of x squared is 2x. We already have a 2 here, so it's 4xy. Then the electric field is going to be -4xy in the ax direction. And we are going to differentiate with respect to y. The derivative of this with respect to y is 2x squared. Okay, we have one y here, it is 2x squared. -2x squared in the ay direction. And the derivative of this with respect to z is only -5. We have a negative sign here, then it becomes 5az. Okay, so this is the electric field obtained from the potential by applying the gradient. We converted a scalar into a vector using the gradient. Now we want to calculate the value of the electric field at P. The value of E at P is going to be, we simply apply the point, the coordinates of the point. negative 4, 3 and 6. So it is going to be negative 4 times 3 in the AX direction, minus 2 times negative 4 squared in the Y direction, plus 5. We don't have an option here to apply this 6 here because we don't have a variable here, only a number. So it's 5 AZ volts per meter. And with this, we find that the electrical field at P is 48 in the X direction, minus 32 in the Y direction, plus 5 in the Z direction, and the magnitude of the electrical field is the magnitude of the electric field at P is going to be the square root of 48 squared plus 32 squared plus 5 squared, and this is equal to 57.9 volts per meter. This is all for letter B. And this is the magnitude we want to calculate now, the direction of the electric field. Okay, observe that the potential is merely a scalar. Okay, but the electric field is a vector. So vectors have magnitude and direction. We have already calculated the magnitude of the vector. We want to calculate the direction of the vector, and the direction of the vector is going to be the direction of the field at P. The direction of the field at P is going to be found by dividing this number here, okay, the vector, this part here, these numbers, by the magnitude, and the magnitude is this, 57.9. And then we find that the direction of the electric field at P is given by alright? So this is the magnitude of the electric field, and this is the direction of the electric field. And this is all for letter C. For letter B, let's calculate what letter C wants. Letter C wants from us the electric flux density D at P. So let's go do it. Letter C, for free space, we know that the D is equal to epsilon 0 times E. where E epsilon 0 is equal to 1 over 36 pi times 10 to the negative 9 farads per meter. And using this value here and the value of the field that we just calculated, we can find that the electric flux density is negative 35.4 xy in the AX direction minus 17.71 x squared in the AY direction plus 44.3 in the AZ direction picocoulombs per meter cubed. So this is D, okay, the electric flux density. And to find the value of the electric flux density at P, we simply substitute the values. For X, we have an X here and X squared here. You put negative 4. For Y, you put 3. And we don't have an option to put this 6 here for Z, so you leave it the way it is. And you're going to find the electric flux density at the point P, okay? And now, letter D wants us to calculate the volume charge density. And to do this, we are going to use the divergence. Letter D. The volume density of charge is equal to the divergence of D, okay, which is gonna be the partial derivative with respect to x of dx plus the partial derivative of y, the partial derivative of dy with respect to y, plus the partial derivative of dz with respect to z, and dx is this, negative 35.4 xy, dy is this, negative 17.71 x squared, and dz is this, okay? At point P, firstly, V is equal to negative 35.4y picocoulombs per meter cubed, okay? And at P, y is equal to 3. And then the volume density of charge is equal to negative 106.2 picocoulombs per meter cubed. All right? Is everything okay? Did you understand everything? If we differentiate this in x, we get this. If we differentiate this in y, it is 0. If we differentiate this in z, it is 0. Then we are left only with this term here, okay, for y. And at the py is equal to 0, that's why we find this value here. Okay, this is all for exercise 11. Let's go to exercise 12 now. Exercise 12 now. Calculate the capacitance of a parallel plate capacitor having a mica dielectric of relative permittivity of 6, a plate area of 10 square inches, and a separation of 0.01 inches. Okay, this is the exercise, very simple one, and we are going to exercise how to convert from inches to meters. Okay, and the exercise goes like this. The area, the surface area, will be in meters. 10 square inches times 0.0254 squared, which will be equal to 6.45 times 10 to the negative 3 meters squared, and the separation from inches to meters will be 0.01 times 0.0254, which is equal to 2.54 times 10 to the negative 4 meters. And with these values, we can calculate the capacitance, and the capacitance can be calculated using this expression here. Relative permittivity times the permittivity of free space, the area divided by the separation, and we simply compute using the values that the exercise gave us. Okay, 6 times 8.854 times 10 to the negative 12 times 6.45 times 10 to the negative 3, it all divided by 2.54 times 10 to the minus 4, and this is equal to 1.35 nanofarads. Alright, this is the capacitance of this capacitor, having a mica dielectric of relative permittivity of 6. Alright, my friends, this is all for exercise 12. Let's go to exercise 13. Exercise 13, a point charge of 1 nanocoulomb is placed in a space with a permittivity of 8.85 times 10 to the negative 12 farads per meter as shown in the figure. The potential difference VPQ between points P and Q at distances 40 millimeters and 20 millimeters respectively is a very simple exercise, and the potential difference VPQ is going to be the potential in P minus the potential in Q, of course. And this can be calculated by simply doing the following. Q, okay, this charge here, Q divided by 4 pi epsilon 0 and 1 over dp minus 1 over dq. Okay, the exercise gave this, the permittivity. The exercise gave the charge 1 nanocoulomb, and the exercise gave the distances 40 millimeters and 20 millimeters. And applying this on the expression, we get that the potential difference between them is negative 225 volts. Okay? Very simple exercise, exercise 13. Let's go to exercise 14. Exercise 14. A parallel plate capacitor has an electrode area of 100 millimeters squared with a spacing of 0.1 millimeters between the electrodes. If the charge on the capacitor is 100 volts and the dielectric is air, calculate the energy stored in the device. Okay, these are the data given by the exercise. We are going to use the expressions here. The energy is a half of CV squared, and the capacitance can be calculated using the permittivity of space times the area divided by the separation, which is 8.85 times 10 to the minus 12 times 100 times 10 to the minus 6 divided by 0.1 times 10 to the minus 3, and this gives 8.85 times 10 to the negative 12 farads. With the value of the capacitance, we can use this expression here for the energy, and the energy is a half times 8.85 times 10 to the negative 12 times 100 squared, which is 44.3 nanojoules. Okay, a very simple exercise. All you need to know is these two expressions here, and be able to use them to find the energy stored in the capacitor. This is all for exercise 14. Let's go to exercise 15 now. Another very simple exercise. Let's go to exercise 15. A composite parallel plate capacitor is made up of two different dielectric materials with different thicknesses, T1 and T2. As shown in the figure, the two dielectrics are separated by a conducting foil in the middle here. The foil is in the middle here. Calculate the voltage of the conducting foil. Alright, we want the voltage here in the middle between the dielectrics. Alright, the relative permittivity of dielectric 1 is 3, and the relative permittivity of dielectric 2 is 4, and these are the thicknesses. We are going to use this expression here. C, the capacitance, is equal to the relative permittivity times the permittivity of free space times the area divided by the separation. Okay? And when capacitors are connected in series, charge will be evenly distributed on them, which means that Q1, the charge in dielectric 1, is equal to the charge in dielectric 2. Okay? Which means that capacitance 1 times 100 volts minus V is equal to C2 times V. And this capacitance here, capacitance 1, can be found by using this expression here. permittivity of free space times the relative permittivity of dielectric 1 times the area divided by the thickness multiplying 100 minus V will be equal to E0 epsilon R A over T2 times the voltage that we want to calculate, the voltage at the foil. And substituting the values, these values here, and here, we find that V is equal to 60 volts. Okay, the voltage of the conducting foil here, this is the foil. The voltage at the conducting foil is 60 volts. Okay? To calculate this, we assumed that the charge will be evenly distributed when the capacitors are in series like this, okay? And we used this expression here to calculate the capacitance. And by substituting this and this here, we found 60 volts. So this is everything for exercise 15. Let's go to exercise 16. Exercise 16. A parallel plate capacitor is made of two square metal plates of 400 millimeter sides. The 14 millimeter space between the plates is filled with two layers of dielectrics of relative permittivity, 4 for dielectric 1 and 2 for dielectric 2, and their thicknesses is 6 millimeters for dielectric 1 and 8 millimeters for dielectric 2. And with this data, the exercise wants us to calculate the capacitance of this capacitor. Alright, as they are connected in series, it is the inverse of the resistor, okay? It is as if capacitors in series behave as resistors in parallel. So the equivalent capacitance is going to be C1, C2 divided by C1 plus C2. We use frequently this expression for resistors in parallel. The product divided by the sum. But for capacitors, this expression is valid when they are connected in series. This is what I wanted to mean. And the capacitance C1 is equal to the permittivity of free space times the permittivity of dielectric 1 times the area divided by the separation or their thickness. And this is, we are going to calculate the area, okay? The thickness is the exercise already gave, and using these values you find a capacitance of 94.4 times 10 to the minus 11 farad, and for the capacitance of the second dielectric we find the permittivity of free space times the relative permittivity of dielectric 2 A over D D2, and using the values we find 35.4 times 10 to the negative 11 farads. And to finish, we need to use these values in this expression here to calculate the equivalent capacitance. And the equivalent capacitance is 257 picofarads. This is the solution of exercise 16. Very simple, isn't it? Let's go to exercise 17. Exercise 17, calculate the divergence of the vector field V of x, y, and z equal to the negative of x times the cosine of xy plus y in the x direction plus y times the cosine of xy in the y direction plus the sine of z squared plus x squared plus y squared in the z direction. Okay? To calculate the divergence of this vector field, we use the expression. The divergence of V is the partial derivative of Vx with respect to x in the x direction plus the partial derivative with respect to y of the vector, the component of the vector in the y direction, plus the partial derivative with respect to z of this, the component of this vector field in the z direction. Alright? And the divergence of this can be calculated by applying this. What is the component of this vector field in the x direction? Is this. Okay? All we need to do is to differentiate this with respect to x. And what is the component of this vector field in the y direction? This. We simply differentiate this with respect to y. And the component of this vector field in the z direction is this part here. We simply differentiate with respect to z. And by doing this, we get that the divergence of this vector field is 2z times the cosine of z squared. Okay? A very simple exercise just to practice calculating the divergence of a vector field. Now let's go to exercise 18. Exercise 18. A solid sphere made of insulating material has a radius capital R and a total charge Q distributed uniformly in its volume. Calculate the magnitude of the electric field inside the sphere. Okay, my friends, let's go to the solution. Observe that now we want to calculate the electric field inside of the body. We are accustomed to calculating the fields outside of the charged body. We want now to calculate the electric field inside of the charged body. And to understand how to do this, we need to understand how this portion of the sphere inside relates to the entire charged sphere. Okay, so the flux is going to be equal to the encircled charge, not the entire charge. The entire charge was given to big Q. The encircled charge, only the charge within this smaller radius here, this smaller sphere, will be equal to the closed surface integral of the flux density ds. Okay? The relationship between the total charge and the encircled charge is proportional to the volume. For the total charge, we have a greater volume. For the encircled charge, we have a smaller volume. And then the encircled charge is going to be Q r cubed over capital R cubed. Okay? Therefore, we are going to use this expression here. Okay? Q r cubed over r cubed is going to be equal to this integral here. All right? And this integral here is equal to 4 pi r squared times d. And using this and this, we discovered that d is equal to q r over 4 pi r cubed. And from the flux density, we get that the field is equal to QR over 4 pi epsilon 0 r cubed. Okay? This is the expression. As the exercise didn't give us any numbers, we are going to let it expressed in this way here. So this is the electric field, okay, inside of this charged sphere. This is all for exercise 18. Let's go to exercise 19 now. Exercise 19, 2-point charges Q1 and Q2 are placed at coordinates 1, 1, 0 and -1, -1, 0 respectively. The charge of Q1 is 10 microcoulombs and the charge of Q2 is 20 microcoulombs. Calculate the total electric flux passing through the Z equal to 20 plane. Okay? This is what the exercise wants us to calculate, the total electric flux that passes here. Okay? And as the charges are of similar polarities, the flux will go up like this. And down, because they repel each other. The exercise wants us to calculate this flux here. Okay, let's do it. Let's calculate what the exercise wants us to calculate. Gauss's law states that the total electric flux through any closed surface is equal to the total charge enclosed by that surface. So Gauss's law states that the flux is equal to the enclosed charge, which is equal to the closed surface integral of the flux density with respect to a surface. Half of the flux passes through the plane. Half of the flux passes through the Z20 plane, and half of the flux passes through the negative Z20 plane. Okay, so the flux at Z equal to 20 is going to be equal to a half of the enclosed charge, and this is equal to 20 plus 10 divided by 2, which is simple and equal to 15 nanocoulombs. Okay, a very simple exercise. This may scare you because this is a surface integral, but if you understand the concept, you can simply calculate it using this expression and find 15 nanocoulombs as the flux. Okay, because the flux is equal to the enclosed charge, and we don't want the entire flux here and here. We want only half of it because we are computing to the Z20 plane and not the negative Z20 plane. Okay, so this is all for exercise 19. Let's go to exercise 20 now. Exercise 21. Suppose that a magnetic field equal to 0.2 z squared in the ax direction for z greater than 0 and h equal to 0 elsewhere as shown in the figure. Calculate the line integral of h dl for a square path with sides centered at 0, 0 and z1 in the y equal to 0 plane, where z1 is equal to is greater than 2 times d. Okay, these are the conditions that the exercise gave us. The field is 0 elsewhere, and due to this expression above z equal to 0. So for z greater than 0, the field is given by this expression here, and we need to calculate this for this square path centered at z1 if z1 is greater than 2d, where d is the side of the square. Alright, let's do it. Let's calculate this line integral here. Firstly, at the top here, at the top, is going to be 0.2. We are going to follow this expression here, 0.2 times z squared, where z is equal to z1, which is the center, the point that locates the center of the square, plus half of the side. Times the entire length here, okay? And at both sides here and here, we have 90 degrees 90 degrees with the direction of the field. Okay, the field goes in this way, and the direction of the differential element of a line is in this direction, and a dot product for an angle of 90 degrees is 0. So at the sides, this line integral here is 0, and at the bottom, this is going to be negative 0.2, because Z1 minus a half of D squared times D. Okay? Why this negative sign here? Because here at the top, the direction of the differential element is in line with the direction of the field. Here at the bottom, the direction of this line element here, this DL, is in the other direction. So they make up an angle of 180 degrees, and when vectors are in the same direction, the dot product is 1, and when they are in opposite directions, the dot product is negative 1. Okay, for the entire path, this line integral here becomes 0.4 Z1 D squared. Okay, this is what the exercise wanted us to calculate, and this is the solution of exercise 21. Let's go to exercise 22. Exercise number 22, calculate the force on a square loop of wire in the z equal to 0 plane carrying 2 milliamperes in the field of an infinite filament on the y-axis conducting 15 amperes in the negative AY direction. Okay? There is this current here flowing in a filamentary conductor in the negative AY direction, and there is a square loop of wire for Z equal to 0 conducting 2 milliamps of electricity. So this is immersed. Observe that this current is much greater than this current here. Alright? Then the magnetic field created by this current here is much stronger than the magnetic field created by this current here. And we are going to understand the problem as this square loop of wire immersed in the magnetic field created by this current here. Alright? And we want to calculate the force on this square loop of wire here due to the field created by this current here, 15 amps in the negative y direction. And the force will be calculated by the force is equal to negative y times the line integral of b vector dl, or b cross dl. Alright, but before using this expression, we need to find b, okay? B is the magnetic flux density, and let's calculate B. The magnetic field is I over 2 pi rho, a phi, okay? Because why phi? Because we know that for a filamentary conductor, the magnetic field goes in this direction here. It surrounds the cable, and since it is in the x direction, see this, that this filamentary conductor is laid in the y direction, and this loop here of wire is displaced in the x direction, okay? It is displaced in the x direction. So this rho here can be understood as 2 pi x az, okay? Because the force is going to be in the z direction here. Alright? And doing this calculating, we find that it is going to be 15 amperes over 2 pi x in the az direction. And we know that B is equal to nu zero H. This is the relationship between the magnetic field and the flux density. And while this nu zero here is the magnetic permeability of free space. And using this and this, we know that B is equal to 3 times 10 to the negative 6 divided by x az Tesla. And we are going now to use the expression of the force to calculate the force on this loop of wire due to this filamentary conductor laid in the y direction. And we find that F is equal to negative 2, okay? Observe the difference. Here, the creator of the field is this current here. But when we want to compute the force, we already used this current here for the flux density. We need to put here now the current flowing in this loop of wire here, okay? 2 times 10 to the negative 3 amperes times 3 times 10 to the negative 6. And now the integrals, the integral from 1 to 3 of az over x, okay? Here, az over x, okay? We treated this as a constant and we put it out of the integral. in a cross product with dx ax, okay, we are integrating first this part here, and this segment here goes in the positive direction of the x-axis, plus the integral from 0 to 2 of az over x in a cross product dy ay. Now we are integrating this part here, okay, and this part here is in the positive y direction, okay, and plus the integral from 3 to 1, okay, this here is 3 and this here is 1, okay. And in the y direction, this here is 0 and this here is 2. This is how it varies in the x and in the y direction. AZ x in a cross product with dx ax. Okay, observe here that I inverted, and I'm integrating from 3 to 1, okay, from 3 to 1 here. I could have done this. I could have integrated from 1 to 3, but here I would need to account for the negative sign, and I would need to put a negative 1 here to symbolize that we are integrating in the negative x direction. This is the positive x direction and this is the negative x direction. And the same can be done from in the y direction. We are going to integrate from 2 in y until 0. From 2 in y until 0. Az over x in a cross product with dy ay. One more time, I calculated it in this way. I could have chosen to integrate, if you prefer, if you have studied this and this news to you, I could have integrated from 0 to 2 and to account for the direction. We are not integrating in the y direction from 0 to 2. Observe that we are integrating from 2 to 0. Okay? We integrate first from 1 to 3 here in the x direction. Then we integrate from 0 to 2 in the y direction. Then we integrate from 3 to 1 again in the x direction. Okay? You could do this. You could begin in 3 and end in 1. But if you prefer to put from 1 to 3, you need to put a negative sign here to symbolize that you are going in the opposite direction from 3 to 1. And the same here, you are going from 2 to 0. And if you want to put from 0 to 2, you need to put this negative sign here to symbolize that you are going in the opposite direction. And if you develop all of these integrations here, you are going to arrive at the value of negative 8 ax piconewtons. And this is the force exerted on the square loop by this current of 15 amperes. Okay, this is all for exercise 22. Let's go to exercise 23. Exercise 23, for the rectangular loop of wire shown in the figure, calculate the torque. We want to calculate the torque due to the magnetic force, and the torque can be calculated using this, okay, the expression of the flux density here, negative 0.6 in the y direction and 0.8 in the z direction, and the value of the current, which is 4 milliamperes, and the torque will be calculated using this formula here, which is 4 times 10 to the negative 3 amps times 1 meter by 2 meters in the z direction, in a cross product with negative 0.6 y plus 0.8 az. Okay, the torque can be calculated as the current times the surface area, but this surface area here has a direction. It is not simply a number that represents the surface area. It has a direction, the AZ direction, okay, the AZ direction, in a cross product with this field here. And if we develop this, we can find that the torque is equal to 4.8 times 10 to the negative 3 in the AX direction, Newton meters. Okay, the torque will be in the X direction, in the positive X direction. And this is all for exercise 23. Let's go to exercise 24. Exercise 24. Given a ferrite material operating in the linear mode with the magnetic flux density of 0.05 Tesla, calculate the susceptibility, magnetization, and the magnetic field if the relative permeability is 50. Okay, this is the question. Let's solve it. The solution will be, since the relative permeability is related to the susceptibility as 1 plus xm. Okay, so we use the value of 50 and discover that the susceptibility is equal to 49. Very easy, very easy. And to calculate the magnetic field, we use this expression here that relates the magnetic field with the flux density, which is nu r times nu 0 times h. Okay, and with these values we get that the magnetic field will be equal to 0.05 divided by 50 times 4 pi times 10 to the negative 7, which is 796 amperes per meter. And finally, the magnetization is related to the magnetic field as follows. which is the susceptibility times the magnetic field, and this is going to be 49 times 796 amperes per meter, and then the magnetization is 39,000 amperes per meter. Okay, my friends, very easy exercise just to practice the concepts of relative permeability, susceptibility, and magnetization. Let's go now to exercise 25. Exercise 25, calculate the self-inductances and the mutual inductances between two coaxial solenoids of radius R1 and R2 with R2 greater than R1, carrying currents I1 and I2 with N1 and N2 turns per meter respectively. Okay, this is the exercise, and the solution will be, let's calculate the mutual inductances first. For a solenoid, the magnetic field is Ny over D in the Z direction, and if N is equal to N over D, which is turns per meter, we're going to use that for conductor 1 or the solenoid number 1. The magnetic field can be written as in the AZ direction. Here, the AZ direction is the direction of the radius, very, very much inside of the solenoids. For okay, inside of the solenoid, and this is 0 outside. And for solenoid 2, the same. And 0 outside. Okay, we're going to use these expressions. The flux can be calculated as the double integral of the flux density with respect to a surface. Okay, and if we partition, if we have a surface here, this is going to be the orientation of this integral here. Okay, and then flux 1, 2 will be equal to nu 0 N1 I1 pi I1 squared, which gives a mutual inductance of M12 equal to nu 0 N1 and 2 pi R1 squared. This is the mutual inductance. Okay, the mutual inductance is equal to N2 phi 12 over I1. Alright? We use this here to calculate this, the mutual inductance. And you can use values here. This is just the expression. And now for the self-inductances, we use that the flux is going to be nu 0 and 1 I1 pi I1 squared, and the inductance is going to be nu 0 and 1 squared S1 D. If we want this per unit of length, the inductance per meter will be N1 squared S1. This is inductance of the solenoid number 1. Alright, and you can play with numbers here, you can put numbers here and here to understand the mutual inductances and the self-inductances. And this is the idea of exercise 25. Now let's go to exercise 26. Exercise number 26 now. Two conductors are carrying currents in opposite directions as shown in the figure. Calculate the magnetic field at point P. Okay? This is conductor 1, which carries current in the direction entering the board, and the current is I, and this conductor here carries current going in this direction from the board, and the current is negative I. This is positive I, this is negative I. We want to calculate the magnetic field at P. So let's do it. For the conductor carrying this current here first, the To finish, let's go to a simple exercise. Exercise 27 wants us to calculate the inductance of a long solenoid of length 1000 millimeters wound uniformly with 300 turns on a cylindrical paper tube of 60 millimeters of diameter. So the diameter is 60 millimeters. And the solution is we simply apply this expression here of inductances for solenoids. This L here is the inductance, and this little L here is the length of the solenoid. And we simply use the numbers 4 pi times 10 to the negative 7 times 3000 squared times pi times 30 times 10 to the negative 3 squared, it all divided by the length, which is 1000 times 10 to the negative 3, and we find a value for the inductance equal to 32 millihenry. Very easy exercise. Okay, my friends, this was the video that I wanted to make to show you some exercises that frequently appear in exams for electrical engineers, both in college and for civil service. And I hope you enjoyed it and learned from it. I am a teacher. If you want to book a lesson with me, use my WhatsApp number, guys. Goodbye!